Hello, linear algebraists. This is the question that I kind of messed up in class. I couldn't come up with a decent explanation in a reasonable amount of time, and instead of being confused, while everybody waited for me to be confused and a little creative, I decided in class to make a video for it instead. So here that is. Sorry I didn't get to it until today because I had kind of a busy weekend, but anyways, here we are. Here's the question written out, and I also just wrote down all of the facts that you're allowed to assume here, which is a good habit whenever you're writing a proof, just so it's clear to you what you know about the objects that you're talking about. So in this case, the objects we're talking about are T is an invertible linear transformation, and I just copied down the definition of an invertible linear transformation over here, so it's easier to see. And we're given two functions, two functions s and u that have this property, that s of t of x cancels out and gives you x, and u of t of x cancels out and gives you x for any vector x in Rn. And I changed some of the letters around here to make it clear. It originally said, given any v in Rn, we can write v equals t of x for some x. The problem was that this x here was not the same as that y, as this x over here. So I just called it y instead of x to make it maybe a little easier to read. And also, in the definition of a linear transformation, this was originally called s, was this function that does like the inverse of t thing. But this s wasn't the same as the s over here, so I renamed that to q to hopefully make things a little easier to read. Anyways, here's a point to pause it and make sure you understand all of this, so it'll make the explanation make more sense if you read it carefully. And after you've paused it and read it, I'm just going to go on right now. So how do we show that v, given any v in Rn, and I'm saying let v be any v in Rn because we want to show that something is true for all v in Rn. So you should be able to take any v in Rn is a good way to start a proof about all v, is just write that down. Anyways, how do you know that v is equal to t of y for some y in Rn? The trick is from the definition of a linear transformation. This part 2 here, the second equation, says that for any vector in Rn, t of q of that vector equals that vector. So how do we know that v, if we pretend that this v is the x that you're talking about here, how do you know that you can make this work? Well, actually, if the answer to this question is yes, because if you say y is q of v, and you know this function q exists because you're assuming that t is invertible, so this definition works. So y is equal to q of v works because the definition says that function q exists and it cancels out with the function t in this way, so t of q of v must be equal to v. So yes, that means that t is onto, no matter what v you pick in the codomain of t, there is a y, also known as q of v, in the domain of t that makes t of q of v equal to v. So now that you have that, we can use this y and plug it in, and plug in t of y in place of v here, because those are equal. And then when you do that, we can use the assumption that we made here, that u of t of x is equal to x for all x in Rn. That also works for this y here that we have. And so yeah, you just get y, also known as q of v. And then you could also plug that into s. The same thing happens. S of t of y is going to cancel out in the same way because we assume that that works for all vectors there. And that means you also get the same thing, q of v. So what this means is that no matter what vector in Rn you plug in to U or into S, you get the same thing out, which is the same thing as Q of V, where Q is the function that must exist because you're assuming that T is invertible. So yeah, that means you get the same output when you plug V into both of those. You could also just say based on that U and S are the same function. And also, you're getting the same thing as Q. So you can say Q is the same function as that too. So what this proves is that if there's a function that cancels out with t in this way, that cancel, like if you do s of t of x and you get x, or you do another function u of t of x equals x, and you're assuming t is invertible, and the definition of invertibility says there exists this other function q, it turns out they all give you exactly the same output, no matter what v you plug in, no matter what vector in Rn you plug in. So that means they are the same function, and that's why you usually write it as just t inverse. That's a nice thing here. We don't have to come up with all of these different names for different inverse functions. There's only one, and that's why you usually just write it as t inverse instead of as u or s or q or something. So that is a nice thing about inverses. So anyways, that is the explanation for that. Hope your studying for the midterm is going well, and I'll see you in class tomorrow.